Hello everyone. This is section 5.2, normal distributions, and here we're going to find probabilities when we need to calculate z-scores first. So last time we saw how to find areas given the z-scores. Now we're just going to add one more step, and that's finding the z-score first. So when the variable is normally distributed, we can find the area. Remember, I like to use the term area, but area is synonymous with probability, percentage. Typically we give it as 4 decimal places, and we noted that here that area, probability, or percent can be used interchangeably. And when we're given an x value, it's raw data or an actual data value. And recall that the z-score represents the number of standard deviations that this data value lies away from the mean, population mean, of course. So some procedures if you wanted to, although as we go through these examples, they should flow rather neatly without having to use this little cookbook recipe. But first we're going to identify the mean standard deviation and any data values, or I like to call them critical values, that are important. Sketch the normal curve and shade the desired area, but we're going to label it initially with respect to x, and then we're going to calculate z-scores. And remember the z-score formula, it's given on our table, or on our formula sheet, that is, or key formulas. You should have printed this and use this on quizzes and tests and such. And it's given in terms of words and in terms of symbols, so get used to the symbols. And that's all we'll be using in this section is x minus mu over sigma. So x being the data value, minus mu, the population mean, divided by sigma, this population standard deviation. And so a procedure, if you want, continuing, is after you find the z-scores, find the left cumulative areas. We're used to doing that. And then determine the area of the shaded region. So 4 and 5 are basically what we did in section 5.1. So this particular problem assumes that it's normally distributed, so that you have to be told that, and you typically will always be told that. And then we're told that the mean is 120, and that the standard deviation is 15, both being population mean and population standard deviation. And notice that this wants the probability that x, the data value of x, is less than 112.5. So the first thing to do is to calculate the z-score for x being 112.5. Now, let me go to a sketch first. When I make my sketch now, I draw the standard normal distribution, or I should say, the normal distribution, as we always do. But now the mean initially is given to be in terms of x, and that's 112.5. And that's mu. That's 112.5, not x. And our critical value, or the mean is given to be 120. So the mean goes down the middle, and that's given to be 120 in this case. Okay, sorry for that. And the critical value, or the data value of interest, is 112.5, which lies somewhere to the left of the mean. So x, we'll label that as 112.5. And we want the probability that x is less than that, so that's everything to the left of that data value, or everything that's in the little left tail. Now, what we're going to do is we're going to transform this data value into a z-score. We don't need to compute the z-score for the mean because we know the z-score for the mean is 0. Now, some people will draw a separate distribution. I just put the z's right below the x's, okay? So I know the z-score for the mean is 0, and now I calculate a z-score for 112.5. So again, the formula, x minus mu over sigma. In the future, I won't be writing that. We'll just go right to it. So data value x, 112.5, minus the population mean, 120, over the standard deviation was 15. And so go to your calculator. Make sure you press equals after you do the subtraction before you do the division. And we get a z-score of negative 0.5. But any z-score we want to report to 2 decimal places, so negative 0.50, and that's because that is what we consider in table 4, is the z-score to 2 decimal places. Now, I would assume that you're comfortable with table 4 based on what we did in the last unit, or excuse me, section. But if you like negative 0.50, again, you got to be a little bit careful with this, because remember the 0 is all the way to the right, okay, kind of like a number line, the way the negatives are constructed. So negative 0.5, that row intersected with 0, 0 is 0.3085. So 0.3085 is the area to the left. Of that data value, and consequently that's the area we're looking for. So if you want to write probability, now here's the notation that you could use. You could say the probability that x is less than 112.5 is the same as the probability that z is less than negative 0.50, which is going to be what we found in the table, 0.3085. But in the future, you might just see me write area, okay, rather than using the probability notation. So the probability notation is fine, but if you want to make things a little bit easier, you could just call it area. All right, going to the next example, x is greater than 140. So again, we proceed in a standard fashion, no pun intended, right? Because we're talking about the standard normal distribution. Okay, that was just a joke. So here's my normal distribution, but initially I label it with regards to x. Now we're working off the same mean and the same standard deviation. So the mean again was 120. We don't worry about labeling standard deviations. We just worry about the critical value, or the x value of interest. That's 140, which is somewhere to the right of the mean. So x equals 140 is over here. We want everything greater than that. So that means what's in the right tail. Now, when we ultimately look up in table 4, the z-score for 140, remember it's the left cumulative area, so we're going to do the little arrow there. We don't have to calculate the z-score for the mean, that's 0. Oh, you know what I should have done? I got a little excited after I did the z-score here. I really should have come back here and said z equals negative 0.50, right, to be consistent. Okay, in any event, now we have to consider calculating the z-score for x equaling 140. So again, it's x minus mu. I'll just jump right to the calculation. X is 140, minus mu is 120, over the standard deviation of 15. Okay, that comes out to be positive 1.333 repeated, but we'll round to 2 decimal places, so 1.33. And I should actually come back here and label that on my standard normal distribution. So now we standardized. And now the area or the probability that we're looking for is going to be 1 minus, because we're looking for the area to the right. So 1 minus, oops, I got to look up the area first. So looking up 1.33, again, I'm not going to, this will be the last time I go to the table 4, because I have to assume that you're comfortable with using it. And 1.33, go down to 1.3, over to 0.03, we see 0.9082, and so that's my left cumulative area, 0.9082, and the area I'm looking for is, again, its complement, right? 0.1 minus 0.9082, which is 0.0918. Okay, so 3 classic situations. To the left is the area in the table, to the right is 1 minus, and now we see between these two values. So again, you want to proceed by drawing the normal distribution, labeling the mean down the middle. So that was mu equals 120. The two data values are 110, which is somewhere to the left of the mean. Again, it does not need to be to scale. And 150, which is somewhere to the right of the mean. Okay, I like to draw the arrows right away. And what we're looking for is everything in between. And so now we need to do 2 z-scores. First, for x equaling 110, we have z is x minus mu over sigma again. So 110 minus 120 over 15 gives 0.66666 negative. So round to 2 decimal places, negative 0.67. And then we have to do it again for 150. And so z is 150, the data value, minus the mean of 120, over the standard deviation of 15. That gives us 2, but again, we want to round to 2 decimal places. So we'll show the z-score as 2.00. Alright, now to the table. Look up a negative 0.67. Double check this, make sure you know how to use the table. 0.2514. Look up a 2.00. And again, double check this, make sure you know how to use the table. 9772. And because we're looking for what's between the area, and again, you could write out the probability, and then in terms of z-scores, let me just do that one last time. So you could say the probability that x is between 110 and 150 is the same as is equal to the probability that z is between 0.67 and 2.00, and then that's the difference between the two. So always the larger, in this case 9772 minus the smaller 0.2514. And that gives us 0.7258. Now you could be changing these to percentages as well, and in your mind you might want to think about them as percentages when you make conceptual interpretations. Like this would be roughly 72.58%, right? Moving the decimal point 2 places to the right as a percentage. But there's the 3 classic situations. Once again, if you're looking for area to the left, it's the area that you find in table 4. If you're looking for the area to the right, it's 1 minus the area you find in Table 4. And if you're looking for the area between, it's the difference between the two values that you find in Table 4. So now we consider looking at word problems. So your favorite. I'm being facetious when I say that because I know students generally frown upon word problems. But keep in mind that you're looking for three key things. First off, that the variable is normally distributed, and that you could pretty much guarantee will be stated. And then you're looking for the mean and the standard deviation. And so maybe read the problem over and then pick it apart, but it indicates that people use their computer as an average, so the average represents the mean of 2.4 years. So I'm going to write this as the given. So I'm given here, besides the fact that it's normally distributed, which I won't even bother commenting on, we're given that the mean mu is 2.4. And it states the standard deviation. So that's sigma is 0.5 years. You select a computer owner at random, find the probability that this computer owner will use their computer for fewer than 2 years. So here's where you might want to consider writing the probability formula. We want the probability that x fewer means less than 2. So we're going to draw the normal distribution. And again, initially label it to be with respect to the data value and the mean. The mean goes down the middle, mu is 2.4. The critical value of interest is x equaling 2, which is to the left of the mean. And we want everything less than that. So shade in the left tail. So now I'm going to put the arrow there to the left and calculate the z-score. So 4x equaling 2. Again, our z-score formula is x minus mu over sigma. So here we have 2 minus 2.4 over 0.5. So that gives us a z-score of negative 0.8. And again, I'm going to add an extra 0. And then we go to table 4. And we see an area of 0.2119. So labeling that on our sketch, we see now, if you want to be formal, probability that x is less than 2 is the same as the probability that z is less than negative 0.80, which is that probability that we found in table 4, the 2119. Okay, here's another example. Going to the supermarket, on average, they spend 45 minutes. So we're given u is 45, and here's our standard deviation, 12 minutes, so sigma is 12. mention normally distributed as they always will. And in parts here, first part, probability the shopper will be in the store between 24 and 54 minutes. So we want the probability, if you want to say want, probability that X is between 24 and 54. Okay, so we draw the normal distribution again. Label with respect to X initially. Oh, see, I got a little bit so excited up here. I forgot to do the labeling of the z-scores in this example. Let's go back and do that. Mu was 0, or mu has a z-score of 0, excuse me. I even forgot on the previous page. And this z-score was negative 0.8. Okay, now you don't have to do that, but I think it is good practice. Okay, so the mean mu is 45. Now we've got two critical values. One x equaling 24 to the left of the mean, one x equaling 54 to the right of the mean, and we want everything in between. So let me draw the cumulative arrows, the left cumulative arrows again. It's going to be the areas from table 4. I'm going to start labeling the z-scores so I don't forget. Hopefully I won't forget. Okay, and we need two z-scores. First off, for x equaling 24, we have z is x24 minus the mean 45 over the standard deviation of 12. So z turns out to be negative 1.75. Negative as we would expect, right? So let's label that. And if you want to go to table 4 right away, again, double check so that you're comfortable using table 4.0401. And then do the z-score for x equaling 54. I mean, see, you could do a lot of extra writing. You could say here, then table 4 gives 0.0401. So if you want to do that, that's fine. Okay, calculate the z-score for 54. So we get 54 minus 45 over 12. And that gives a z-score of 0.75. So then again, table 4 gives us 0.7734. So I'll label that in our diagram. Okay, and then I'm just going to start saying area. If you want to use that probability notation, that's great, but area is sufficient enough. And since I'm between, if I want to be complete, I'll label this negative 1.7. Nope, that was the 0.75, positive. Okay, so that's being complete. And the area would be the difference, because we're between. Always the larger, in this case 0.7734, minus the smaller 0.0401. So the area we're looking for, probability 7333. Alright, then the second part says find the probability the shopper will be in the store for more than 39 minutes. So again, well, if you want to write out the probability notation, probability that x is greater than 40, 39. Same mean and standard deviation. So mu down the middle is 45. Okay, that's going to give me a z-score of 0. What's max value? 39. Somewhere to the left is x equaling 39. We'll transform that to a z-score. But we want more than. More than means to the right. So shade in the area to the right of that. And do the calculation of the z-score for x equaling 39. We have z is x39 minus the mean 45 over the standard deviation of 12. Gives us a mean of negative 0.5. I'll add a 0 there. And then we go to table 4. And that gives us 0.3085. So let me label that with my left cumulative arrow. But notice that we're looking for everything to the right of that. If you want to use probability notation again, that's fine. I'm just going to say area. And to the right would be the complement of the area we find in the table. So 1 minus 0.3085 or 0.6915. Now sometimes we ask this question, the how many question. And how many is just taking that probability and multiplying it by the total number. So if 200 shoppers enter, how many? Well, that's the percentage that do stay for more than 39 minutes. Notice we're working off of the answer in part B. More than 39 minutes characteristic. So therefore, take the 0.6915 and you just multiply by the 200. In this case, we get 138.3. So then I'd guess, well, you can't have 0.3 of a shopper. So how many would we expect? No matter what this is, you would round down because we didn't reach the 139 yet. So even if it were 138.7, we'd still round to 138 because you can't have 0.7 of a person doesn't make a full person. Okay, so not to be redundant, but there's a couple more examples that I think you'll find to be very similar, so just extra practice here. Got a classic IQ question, mean of 100. So given U is 100, standard deviation is 10. Sigma is 10. If you want to be a member of Mensa, you have to have an IQ of 120 or higher. So we want to know how probability you would qualify for Mensa. And we want the probability that the X value is greater than 120. Okay, so again, we'll proceed in the standard way of drawing the normal distribution. Initially labeling it with respect to the mean, mu, and the data value of interest, 120, to the right of the mean. We want everything greater than, so in the right tail. So if you want to extend this to make it look a little bit more tailish, that's fine. But I'm going to do the left cumulative arrow right away. I'll label my z equals 0 here. I'll try to remember to fill in that z-score. Usually I get so excited once I find the z-score I forget to go back and label that. But for x equals 120, we have, again, our z-score formula. Hopefully you've memorized it by now. X minus mu over sigma. 120 minus 100 over 10, we get 2. I'll say it's 2.00 because then when we go to table 4, the area we find is 0.9772. Okay, so let me label that z-score is 2.00 and my area is 0.9772, but that's not the area we're looking for. We're looking for the area to the right, so that's the complement, 1 minus 0.9772, which gives us 0.0228. Which is really just about 2% of the people, right? 2.28% of the people would qualify for this high IQ society Mensa that you may have heard of. All right, and then another, again, not to be redundant, but this is just extra practice. Another scenario of the amount of pounds of newspaper that people generate for garbage or recycling is an average of mu equaling 28.3 with a standard deviation sigma of 2.7. We select one household. Oh, there's the assumed normally distributed. And select one household. We want to go between a probability that x is between 25.5 and 27.5. So we'll draw the distribution again. That tail looks a little funny, so let me make it a little bit better. Okay, down the middle of the mean given 28.3. Got two data values, 25.5. That's to the left of the mean. And the 27.5 is also to the left of the mean. We want everything in between. So shade that in. My two cumulative, left cumulative arrows. Start labeling the z-scores for the mean at 0. Then calculate them for the two data values of interest. I like to call critical values again. So for 25.5, we have z is x 25.5 minus mu 28.3 over sigma 2.7. And that comes out to be negative 1.04. So then if we go to table 4, we see an area of 0.1492. Okay, so let me finish my labeling. Negative 1.04 and 0.1492. And then we do the z-score for the other data value, 27.5. I should have said x equaling. I may have said that, but just didn't write it. But we should say for x equals 25.5. And we really should be saying for x equals 27.5. Okay, the z-score would be x 27.5 minus mu 28.3 over sigma 2.7 again. And that gives us a negative 0.30 when rounded. So then we go to table 4 again. And we find that area to be 0.3821. Alright, so now the area we're looking for. Again, you could use the probability notation. Oh, let me label this negative 0.30. And again, if you don't label everything like that, and skip steps, whatever you want. I'm just trying to be complete so it helps you. And the area is the difference, always larger minus smaller. So the 0.3821 minus 14.1492, and it's 0.2329. Okay, so that's the end of section 5.2. So we will see you when you are ready for